Question number 2.30 is a homework which was already given. You have completed this. Okay. So next is question number 2.31. So in 2.31 you have many subdivisions. The first one is two large conducting spheres carrying charges Q, Q1 and Q2 are brought close to each other. Is the magnitude of the electrostatic force between them exactly as given by Q1, Q2 by 4 pi epsilon naught r square, where r is the distance of separation between their centers. So meaning you are having two large spheres. Okay, so there are two large spheres and the distance between the center of the sphere is r. Okay, so in general, in theory, if this r is very large when compared to the radius of the sphere itself, okay, what we can consider is we can consider this to be a point charge. Okay, but here since they are telling that these conducting spheres are very large, that means the radii is comparable to the separation of the two charges. Therefore, what happens when you bring two charges close to each other, which is present on a large sphere? So the charge distribution may vary. Okay, the charge distribution may disturb each other. Therefore, the force of attraction will no longer be your Coulomb's law. Okay, it will no longer be equal to Q1 Q2 by 4 pi epsilon naught r square. Okay, so that is because if the radius is comparable to the size of the separation distance, okay, then no longer Coulomb's law is applicable. You cannot take these two as a point charge. Coulomb's law is applicable for point charges, okay, not for charges with larger radius. Okay, so that is the answer. So the next one is they are asking if Coulomb's law involved 1 by r cube instead of 1 by r square, will the Gauss law still be applicable? So you know in Gauss law, okay, you have integral of EDS is equal to q by epsilon naught. This is your Gauss law. Now when you have ds here, what is ds? ds means you are integrating over the area. Okay, and area has r square only, square component only you will be getting in area. Now doesn't matter what type of shape Gaussian surface you are taking, finally you will be having some square quantity present in the integral. So the electric field will be something divided by some square. Okay, so here you will have the dependency is 1 by r square only. Okay, but if the Coulomb's law changes as 1 by r cube, then this Gauss law can no longer be used. Okay, so you cannot use the Gauss law for any other power other than 2. Okay, so only for power 2 you can apply Gauss law. For any other type of law or dependency we cannot use Gauss law. Okay, so if Coulomb's law is 1 by r cube, then Gauss law is not applicable. Number C is that they are asking whether if you have a charge, okay, and if you release the charge in the presence of an electric field, okay, you are keeping the charge in the presence of an electric field. So what will happen to the movement of the charge? How will the charge move? Whether it will move in a straight line, whether it will move along the line of force of the field, that is what they are asking. So if the line of force of the field is like this, okay, so they are asking whether the charge will be moving along this direction. Okay, whether the charge will be moving along this curved line. So the answer is no, not necessary. Only if the electric field is a straight line, okay, the charge will be moving along this line. The electric field actually gives the direction of the acceleration, okay, of the particle and not the velocity. It does not give the direction of the velocity, it gives only the direction of the acceleration. So the direction of the velocity for this will be something else. Okay, so at any point this is the direction of the acceleration of the particle and not the velocity. Okay, so the charged particle might move in some other path. This line of force represents only the direction of acceleration and not the velocity, and velocity or direction only is displacement. Okay, displacement and velocity have same directions, whereas acceleration is change in velocity, which direction it has changed, that direction is the direction of acceleration. Okay. Number D is that what is the work done by a charged particle or by the electron moving in a nucleus? That is the question, right? Let me check. Work done by the field of a nucleus in a complete circular orbit of the electron. So if it is a circular orbit, okay, we know very well that if this is a center nucleus, okay, so what happens is the centripetal, the Coulombic force will be acting as the centripetal force, and at any point the direction of velocity of the electron, if for example is a tangential direction, then the angle between the force and the displacement, okay, velocity direction is the direction of displacement also, so the force and displacement will be 90 degrees. So what will be the work done? Work done is Fs cos theta. Okay, so that will give us cos 90, which is equal to 0. Therefore, the work done in a circular orbit is 0. Now, what happens if the orbit is elliptical? Okay, what happens if the orbit is elliptical? Now, the theta might not be 90 always. So, in that case, momentarily the work done will be having some value. Okay, so for example, it is going from this point to this point. So, there might be some work done. But eventually, the net work done over a complete circle will be equal to 0 because the displacement in one complete circle is 0. In one complete ellipse, if you move through the ellipse in one full round, okay, then the displacement will be 0 and hence the work done is 0. So anyways, the net work done is 0, but momentarily you might have some value. Number fifth one is that they are asking whether the electric field is discontinuous. So whether the potential also is discontinuous or not. So across the surface of a charged conductor, the electric field is discontinuous. So whether the potential is also discontinuous or not. So potential is not discontinuous because it is a scalar quantity. So that will be the answer for that question. Okay, so since potential difference is a scalar quantity, everywhere it will be remaining as a constant. Okay, so the next question is, what meaning could you give to the capacity of a single conductor? So the capacitance of a single conductor, that is without any plates, that is not bound by anything. Okay, so the capacitance of a single conductor is infinity. So it can store infinite amount of charge. Okay, so practically it is not possible, but in theory we can assume that for a single conductor the capacitance is infinity. In practical it will be, you can call it as very high capacity. Okay, that is the thing. Next question. Guess a possible reason why water has much greater dielectric constant than mica. So water, first of all, is in bent shape. Okay, so the shape of water is bent like this, and the two molecules that are present, the two bonds, OH bonds, are highly polar. Okay, they are highly polar. So because of that property, its dielectric constant is very, very large when compared to any other molecule. Okay, not any other molecule, just we can say that for water generally it is large when compared to most of the molecules. Okay, so that is because, first thing is because it is bent in shape, and the next is because it is highly polar. Okay, and the value for this is 0.6 into 10 to the power minus 29 coulomb meter. Yes, so question number 2.32 is a homework. So 2.33 we have to start. So the question, it is given that you have to design a parallel plate capacitor which is having a potential of 1 kilovolt. 1 kilovolt, and the dielectric strength of the capacitor is given as 10 power 7. Alright, which is having a dielectric constant of 3, epsilon r equal to 3, and you can have a maximum electric field which is equal to 10% of the dielectric strength. So 10 power 7. Okay, and they are asking what is the area that we should have to get a capacitance of 50 picofarad. Alright, so here we will begin with E is equal to V by D. Okay, so here the voltage that they have given is equal to 10 to the power 3 and D we have to find out. E is equal to 10 percentage of 10 power 7. So that is equal to 10 power 6. So V is 10 power 3 divided by D. So therefore D will be 10 power minus 3 meter. Okay, D is equal to 10 power minus 3 meter. Now you have got D, you know the capacitance, you know epsilon naught, you know epsilon R. Okay, you have to find out the area. So capacitance C is equal to epsilon naught, epsilon R, A by D. So what is A from this? C into D divided by epsilon naught, epsilon R. So what is capacitance C? 50 picofarad. So 50 into 10 power 12 minus 12 into D is 10 power minus 3 divided by epsilon naught 8.854 into 10 power minus 12 into 3. Okay, so when you solve this, your answer will be equal to 19 centimeter square. Roughly it is 19 centimeter square. Okay, so that is your answer. You can give the answer in SI units, no issues. Okay, so anything is fine. The next question is 2.34. They are asking us to draw the equipotential surface for different electric fields that they have given. So the first one is a constant electric field in the Z direction. So let us imagine this is the Z direction. Okay, so a constant electric field is acting along the Z direction. So like this, you are having a particular field. So how do you think or how do you imagine the electric equipotential surface to be? So if this is the x-axis, this is the y-axis. So you will have planes which are perpendicular to the z-axis. So that basically it means it is the xy plane. Okay. So all the planes which are parallel to xy are all equipotential surfaces. Alright. So that was the first one. The second one, they are saying that the strength of the field is increasing as it goes to the higher in the z axis. So the strength of the field increases. Alright, so that means you can draw the electric field, the equipotential surface something like this. So imagine this is one plane. Okay, so the next plane is here, the next plane is here, the next plane. As you go above the in the z axis, the planes, the equipotential surfaces come closer because the strength of the field is increasing as we are moving above. Okay, it is increasing as we move above. So the strength of the field, the equipotential surfaces come closer to each other. Alright, so the next question is a single positive charge at the origin. So at the origin you are having a single positive charge. So what will be the equipotential surface? So the equipotential surface is nothing but concentric spheres drawn around the charge, single charge. Okay. So next question, a uniform grid consisting of long equally spaced parallel charged wires in a plane. So you basically have some charged wires which are having positive charges. They are kept on a plane. Okay, so in the mari or plane la vechirukanga. Okay, or a table madri imagine. So they are kept like this. Okay, so I am going to see the front view of this diagram. So the front view will be as if idukku pinnadi apdiye nariya wire vechirukra mari we can imagine. So you are having all the positive charges kept like this. So the wire is going into the board like that. So how you will have the electric field or equipotential surface? So first of all, for a charge, for a single charge it will be like a shell, isn't it? It will be like a shell, but because you are having another charge in between, so they will be what do you call, disturbing each other. Okay, so initially the equipotential surface will be irregular, but as you go away from the charge, okay, as you move away from the charge, what happens is you will get parallel lines or parallel planes which are equipotential in nature. Okay, so the initially it is irregular, and as you move it will become parallel to each other. Parallel planes of equipotential surface you will be getting parallel to the grid. So this is the grid. Okay. Question number 2.35 is regarding Van de Graaff generator. So we don't have that for the syllabus. So we will be doing the next question, which is 2.36. The question goes like this. A small sphere of radius r1 and charge q1 is enclosed by a spherical shell of radius r2 and charge q2. So first you are having a small sphere. So this is a solid sphere. It is having a charge of q1 and a radius of r1. It is enclosed by a charge q2 sphere of radius r2. Then what else is given? So show that if q1 is positive, charge will necessarily flow from the sphere to the shell when they are connected by a wire, no matter what is the charge on q2. So if they both are connected by a wire, alright, if it is connected by a wire, we have to show that if q1 is positive, always the charge will flow from q1 to q2 only, no matter what is the charge of q2. So q2 எந்த charge இருந்தாலும் q1 ல இருந்து q2 தான் charge flow ஆகும் அப்படிங்கறத prove பண்ண சொல்றாங்க. So to prove this, it is enough if we prove that the potential of inner sphere is greater than the potential of the outer sphere. If we prove that much, then we can prove that the charges will flow from inner to outer shell. Alright, so for that we need to find out what is the potential at this point on the inner shell. Okay, so the potential in the inner shell, or first let us find out the outer shell. Okay, so you write down potential on the outer sphere. Potential on the outer sphere will be equal to VR, which is equal to potential due to the charge Q, that is the Q2 charge that is present here. Okay, so we can write VR2 is equal to potential due to Q2 plus potential due to Q1. Okay, because Q1 is also enclosed here. So that will be 1 by 4 pi epsilon naught Q2 by R2 plus 1 by 4 pi epsilon naught Q1 by R2. R2 only we will be writing here, because at this point what is the potential due to this charge and this charge, that is what we are going to find out. Okay, so this can be written as 1 by 4 pi epsilon naught Q1 plus Q2 divided by R2. Q1 plus Q2 divided by R2. So this is the potential of the outer sphere, outer shell. Okay, then what is the potential due to the inner one? So you can write potential on the inner sphere. So that will be equal to V small R1 is equal to potential due to Q1. Potential due to Q1 plus there is a constant potential which is there inside this shell. Okay, because we have studied inside a shell the potential is constant at all points. So at this point also you will be having a potential which is constant value of what is on the outer surface of the shell. So this you have studied in the shell derivation. Okay, potential inside a hollow shell, hollow sphere derivation you have studied. So potential due to Q1 then plus potential due to Q2, that is a constant potential due to Q2 shell. Alright, so this will be 1 by 4 pi epsilon naught, you can take common out. So this will be Q1 by R1 plus Q2 by R2. Okay, because this R2 potential is only present in the entire sphere. Okay, so therefore what we have to do is we have to find out VR1 minus VR2 and we have to prove that it is always greater than 1. Okay, if it is greater than, or you have to prove that this is positive. Okay, greater than 0. Basically you have to prove it is greater than 0. That means it is positive. Adu prove pannu. Okay, so let us write down VR1 and VR2 and then just subtract with it. So we have 1 by 4 pi epsilon naught can be taken outside is equal to into Q1 by R1 plus Q2 by R2 minus Q1 by R2 minus Q2 by R2. Okay, so here this Q2 gets cancelled. So you will be having V R1 minus V R2 is equal to 1 by 4 pi epsilon naught into Q1 by R1 minus Q1 by R2. Okay, so here you can take this Q1 common out. Yes, so if Q1 is positive in this equation, if Q1 is positive, then VR1 minus VR2 will be greater than 0, and hence if the inner potential is greater than the outer potential, that means the charge will always flow from inner to outer, and clearly this is independent of Q2. So it does not depend upon the value of Q2, it only depends upon the value of Q1, and hence we are proving this equation or proving this question. So the last question is 2.37. The top of the atmosphere is about 400 kilovolt with respect to the surface of the earth. They are asking corresponding to an electric field that decreases with altitude. So as you are coming below, okay, near the surface of the earth, it decreases with the altitude. Okay, then near the surface of the earth the field is about 100 volt meter inverse. Why do then we not get an electric shock as we step out of our home, considering your house is an equipotential house is an electro shielded cage? Okay, so in this question they are telling that basically in the atmosphere 400 kilovolt charge is there, and as the height decreases on above our heads usually it will be 100, nearly about 100 volts. So why do we don't feel the electric shock? That is the question. So the answer for that is we are always connected to the ground. Okay, and you know that the earth is an infinite capacitance. Okay, earth has infinite capacitance, so you can give how much ever charge you want to the earth. So what happens when you step outside, even though there is some charge, it will get transferred to the ground, and since you are grounded you are safe, nothing will happen to you, you will not get any electric shock. Okay, next question. A man fixes outside his house one evening a 2-meter high insulating slab. Okay, on top of that they are placing an aluminum sheet. So the next morning he touches the aluminum sheet, whether he will feel the shock or not. So definitely he will feel the shock, because here you are not grounding the sheet. Okay, you are keeping an insulating slab below the sheet. So what happens? So the charges that are accumulated on the sheet will not go to the ground, and if you touch it then you will also feel the electric shock. Next question is, discharging current in the atmosphere due to the small conductivity of air is known to be 1800 angstrom on an average over the globe. Then why does the atmosphere not discharge itself completely in the due course and become electrically neutral? So they are telling basically at some point in the lightning or something, so there is a discharge of the electric current. Now why does the atmosphere constantly have some voltage? Why does it not fully get discharged, and why does it not become neutral? That is what the question is. So the answer for that is, at some part of the atmosphere lightning is happening. Okay, at some part some what do you call this charge discharge is happening. Okay, so it is not, you cannot have complete discharge of the electric field all over the atmosphere at the same time, because at some part of the other you will be having some kind of discharge, and so the average atmosphere will have some potential in it. Okay, so it will never get completely discharged. Okay. What are the forms of energy into which electric energy of atmosphere is dissipated during a lightning? So during a lightning, the energy is in the form of light, heat, sound, etc. Okay, so basically these three, light and heat energy and sound energy. So these three energies, your electrical energy will get converted into. So that is it for the second chapter. You please copy all these questions in your classwork. Okay, and please maintain the classwork properly. So next video I will be uploading about the